Okay, so now moving on to the numerical part of the chapter, we're going to deal with decision trees. So decision trees is a decision support tool that uses a tree-like model of decisions to help companies or managers to come up with the best course of action when the outcomes of the events are not 100% certain. So they're basically a certain probability for an outcome to occur. In that case, we can use decision trees to figure out which course of action yields the best results for the company. So moving on, let's say whenever we're using the decision tool, the decision tree, we have to create nodes, and there are generally two types of nodes. There are first a decision node, right, which is basically if the outcomes are can be selected by the manager itself, or the decision maker has full power as to which option they can decide. The second node is a chance node, where a chance node is a node where the outcomes are actually based on probabilities and the decision taker does not have the power to decide which outcome to select from. For example, in the case of a decision node, it might be if one of you wanted to come to let's say class from your home, you might have a couple of options. For example, hypothetically, let's say that you could either take the public bus, the motorcycle, or you could walk. All right. So out of the three options, you might decide to take the motorcycle. Okay, and you have full control over that. This is not based on probability, but it's basically based on whichever outcome best suits your needs, or is basically what you want. All right. So you have the full power to decide which option or outcome to select from. However, in the case of a chance node, it's a bit different. So let's say you bought a raffle ticket. The lottery ticket, let's say, has a 10% chance of giving you, or let's say of winning $100. Let's say it has a 20% chance, or 0.2, of winning $20, and a 70% chance of winning nothing. Right. So, assuming that these three are the total possible outcomes of this lottery ticket, you could actually calculate something known as an expected monetary value, or EMV in short. The EMV can only be calculated for a chance node and not for a decision node, so that's very important to note. Okay, so the expected monetary value is basically the sum of the outcome values multiplied by the probability of that outcome happening. So the expected monetary value of buying this lottery ticket would simply be 10% times $100 plus 20% times $20 plus 70% times $0. So if you do the arithmetic, that would turn out to be about $14. All right. All right. So now let's look at an example. So this is an example of a single stage decision tree problem where the decision maker has to make the decision only once. All right. So first, let me read out the question. So there's a company called Silicon Incorporated, which is a semiconductor manufacturer, and they're investigating the possibility of producing and marketing a microprocessor. So undertaking this project will require either purchasing a sophisticated CAD, or computer-aided design system, or hiring and training several additional engineers. The market for the product could either be favorable or unfavorable. The company, of course, has the option not to develop the new product at all. With favorable acceptance by the market, sales would be 25,000 processors selling for $100 each. With an unfavorable acceptance, sales would be only 8,000 processors selling for the same price. The cost of the CAD equipment is $500,000, so this would be the fixed cost in this case. But that of hiring and training 3 new engineers is only $375,000, so that's the fixed cost for engineers. However, the manufacturing cost would drop from $50 each when manufacturing without CAD to $40 each when manufacturing with CAD. So the variable cost of while using CAD is 40, while the variable cost of while using engineers is 50. That's what the question is hinting towards, right? So the probability of a favorable acceptance of the new microprocessor is 40%. And the probability of an unfavorable acceptance by the market is 60%. All right. So this is given by the question. So let me just recap the important parts. So if the market is favorable, you have a sales of 25,000. If not, if it's unfavorable, you have a sales of 8,000. The fixed cost is 500,000 for CAD and 375 for engineers. the variable cost for CAD is 40, whereas for engineers is 50. All right, so let's just note that information down and start with the decision tree. So whenever we're starting the decision tree, we always start with a decision node. So we start off with the decision node. We have initially two options. We could either use engineers, right, or we could use the CAD system. Now, if we use engineers, right, the possible two outcomes is that the market could either be favorable or unfavorable, right? So in this case, if the market is favorable, which has a 40% probability, compared to a 60% probability for an unfavorable response. Whereas if you use the CAD system, the possible outcomes is exactly the same, so I can just copy that down there. So the tree structure looks something like this. Now to calculate the value of the outcomes. So if the company decides to use engineers and the market happened to respond favorably, then sales would be 25,000 units, selling at $100 each. So that would total sales of 2.5 million. Now, in this case, out of the revenue now, I need to subtract the cost. So the first cost, I could subtract the fixed cost, which is, in the case of engineers, was 375,000, right? I need to subtract the variable cost, which is $50 each for 25,000 units. So that would be 1.25 million. So if I subtract the variable cost and the fixed cost from the $2.5 million revenue, I end up with a profit of 875,000. That was pretty simple enough. Similarly, I do the exact same thing if the company hires engineers but ends up getting an unfavorable response. If that's the case, then we have sales of only 8,000 units. So our total sales would only be 800,000. The fixed cost would stay the same, and the variable cost, which is 50 for the engineers, times 8,000 would only be 400,000 instead of 1.25, right? So if I were to subtract these two costs from the revenue, I would end up with a profit of 25,000. So what this means is, if the company were to use or select engineers, then they have a 40% chance of making a profit of 875,000, whereas they have a 60% chance of making a profit of only 25,000. Similarly, in the case of let's say in the case of using the CAD software, let's say if the market reacts favorably, then they make a total profit of 1 million. So they have a sales of 25,000 times 100 is 2.5 million. The fixed cost is 500,000, and the variable cost for CAD is 40 and not 50, right, according to the question. So the total variable cost would only be $40 times 25,000 to be a total of 1 million. So if you subtract 1 million and 500,000 from 2.5 million, you end up with a profit of $1 million. Now, what if the market reacts unfavorably? In that case, we end up with a sales of 800,000, fixed cost of 500,000, and a variable cost of 40 times 8,000, which is 320,000. So if you did the arithmetic here, you would end up with a loss of 20,000. So in this case, if the company decides to use engineers, there's a 40% chance of getting a profit of 875,000, whereas a 60% chance of making a profit of 25,000. Whereas if they use CAD, then obviously they can make a profit. They have a 40% chance of making a profit of 1 million, whereas they have a 60% chance of making a loss of 20,000. Now, the next step is to decide whether to use engineers or CADs. Which one is better? All right. To figure that out, the best step is to calculate the expected monetary values for each of these chance nodes. So this is the chance node for engineers, and this is the chance node for the computer-aided design software. So the expected monetary value for engineers is going to be calculated by multiplying the probability with each of the outcome values. So the EMV for engineers is going to be given by 875,000, which is that figure there, times 40% probability from here, plus 25,000, which is the profit for an unfavorable reaction by the market, with a 60% probability. So if I simplified that, I would end up with a expected monetary value of 365,000, which is the expected monetary value for engineers. Similarly, if I did the same thing for the CAD software, then that would be 1 million, which is the profit outcome value, times the probability of that happening, plus a 20,000 loss, which is in negatives here, times a 60% probability, right? So in this case, if I simplified that, I would end up with an expected monetary value of 388,000. So that would be the EMV for the CAD. So out of these two, since the expected monetary value in this particular problem is measuring profits and not costs, right? There's a difference there. We would pick the option that yields us the higher EMV, because the EMV in this question represents profit. So in this case, if I were to pick engineers, then I would be expecting to make a profit of 365,000, whereas if I picked the computer-aided design, I'd be expected to make a profit of 388,000. So in this case, out of these two options, CAD is the better one. All right, so next up, let's look at a multi-stage decision tree problem. So this is a question where the manager has to make a decision more than once. All right, so in this case, the main difference is in the previous question we only had to make one decision, whereas in this question we have to make more than once. All right, so in this case, let me just read out the question and we'll try to figure this out. So a geological survey by an oil company has shown a possible oil reservoir of about 16 million gallons. So two suitable test drilling sites have been identified, which will determine whether or not oil is present. The head geologist of the oil company estimates that the first test site has a 30% chance of striking oil. If no oil is found there, there is still a 10% probability that oil will be found when drilling the second site. If neither test drill finds oil, it is concluded that no oil reservoir exists. It is estimated that each test drill will cost the oil company £2 million. So if the profit from each gallon of oil extracted is £1, should the company make any test drills, and if so, how many? What is the expected profit from this chosen course of action? So there are a couple of numbers here we need to remember. First off, the total here is 16 million. So the total quantity of oil is 16 million, and each of them costs £1. So if they do find oil, the total profit is going to be 16 million pounds, right? There are two test sites, right? There are two test sites. The probability of the first test site being successful is 30%, while the second one is only 10%, right? And each test drill costs 2 million. Obviously, since the profit is $1 per gallon, the total profit, if they do find oil, is going to be 16 million pounds. So, based on this, now we need to figure out what is the best course of action. Should the company make any test drills, and if so, how many, right? That's the question, and we need to solve this using decision trees. So we always start with the decision node, and we initially have two options, right? Either we need to conduct the drilling on test site 1, or the other option is to not drill at all or abandon the project. Okay, so in this case, we could either test drill on site 1 or abandon the project. So if they decide to abandon the project, it's all over, right? There's no expected monetary value, it's going to be 0. But if they do decide to drill on test site 1, now we know that the outcome is actually going to be based on chance. There's a 30% chance they're going to find oil, and a 70% chance they're not going to find oil. Therefore, the node at the end of site 1 is going to be a circular one, which represents a chance node. Now the two possible outcomes of this chance node is either they're going to find oil or they're not going to find oil. Now the probability of them finding oil is 30% and them not finding oil is 70%. So now that if they, let's say, drill on test site 1, they do not find oil, now they have the option of whether or not to drill on the second test site. So this is a decision that they have to make. So since the manager in this case is going to be in full control of whether or not to drill on the second site, it's not based on chance, it's based on the decision. The shape of the node is going to be rectangular, which represents a decision node, right? So once that's done, if they do decide, so in this case, the decision is basically going to be whether to drill on test site 2 or whether not to drill on test site 2, right? So if they drill on test site 2, or the other option is simply going to be to abandon the project. So if they do decide to drill on test site 2, the outcome of whether or not they're going to find oil is also going to be based on chance, right? So in that case, the node here is going to be circular. and the probabilities of finding oil is only 10%, which means the probability of not finding oil is going to be 90%. So in this case, if they do decide to abandon, right? If they do decide to abandon, then their expected monetary value is going to be -2, which means that they did decide to drill on test site 1, so they already have one drilling site or drilling cost incurred, and then they abandon, which means their total outcome value is going to be -2 million. However, if they do decide to drill on test site 1, they do not find oil. Now they decide to drill on test site 2, but then they finally find oil. Then they make a profit of 16 million, which is the let's say revenue of 16 million, minus the 2 test drill costs, because remember they drilled once on test site 1 and then they're drilling again on test site 2, so they have to subtract the cost of drilling twice. So the total outcome value here is going to be 12 million pounds. However, if they do decide to drill on test site 2, let's say, and they do not find oil, then now they've drilled twice on site 1 and site 2, so their total value or outcome value is going to be -4. Okay. Whereas if they find oil in the first drilling site, in the first test site, then their drilling cost is only -2 instead of -4. Therefore, their expected profits is going to be 16 million revenue minus a drilling cost of 2 million, so that will end up with 14 million. Now the next step is to calculate the expected monetary values for each of these chance nodes. You can only calculate EMV for chance nodes and not for decision nodes. Okay, so in this case, the expected monetary value of this chance node is going to be given by multiplying the outcome value by the probability. So in this case, that would be 12 million times 10% probability plus -4 times a 90% probability. So in this case, that would give us an expected monetary value of -2.4 million, sorry. Whereas in this particular case, now let's look at this logically. So if you drill on test site 1 and don't find oil, right? In that case, the expected monetary value of drilling on test site 2 is a loss of 2.4 million pounds. Whereas if you abandon, you make a loss of 2 million pounds. So which one would you rather prefer? A loss of 2.4 or a loss of 2 million? Obviously, you'd prefer a smaller loss, so therefore abandoning would actually make more sense than drilling on test site 2. So the expected so in this case, since you can actually make the decision here, it would be smart for the manager to rather abandon the project rather than drilling on test site 2. So you would cross off that arm and you would pick 2 in this particular case. A -2, sorry, because that's the expected that's the outcome value for abandoning, which is the one you would pick. Now to calculate the expected monetary value of this particular node, that would simply be 14 million, which is the profit, times the probability of that happening, times a loss of 2 million, times the probability of that happening. So in this case, that would be 2.8 million. So that's 14 times 0.3 plus -2 times 0.7, which is 2.8. So in this case, what this signifies is that if the company drills on test site 1, they're expected to make a profit of 2.8 million, whereas if they abandon, they make nothing. So we're comparing a profit of 2.8 with a profit of 0, right? So in this case, obviously 2.8 is a better option. So in this case, the best course of action for the company would simply be to drill on test site 1, right? If they find oil, great, but if they don't find oil, it makes more sense for them to abandon rather than to drill on test site 2. And that would be the best course of action.